I'm also very honored to be here, and today's talk is very meaningful. So for the last few years, we didn't have a chance to meet in person in the campus through the seminar. And last time when I gave a talk here in this room was 2017. It's been already 4 years. Then, ever since then, so many crazy things happen, and that's why I'm here to share all the things happening in my lab today. Thank you so much for coming over here, especially in this difficult time. So I really appreciate your attendance. In return, I try to do my best to entertain you guys today. So let's get the seminar started. So today, I'd like to discuss about our very recent progress on heterogeneous integration of freestanding membranes. What you're looking at here right now is the real single-crystalline gallium nitride. You know what the gallium nitride is, a very useful material in the electronic community. And that perfect 60% gallium nitride is being peeled off from the wafer. So this type of work has been going on for like last 5-6 years in my lab. Then I'd like to share about this progress today. So I name it as a peel and stack because it's kind of like a tape, process to peel the single crystal membrane from the wafer. So that's what I'm going to talk about today. Before going into the full detail about this peel and stack technology, let me briefly go over the future of electronics. So far, electronics and photonic community has been centered around the wafer-based electronics, where we have excellent photonic electron performance on the wafer. But going forward, looking at the future, this high-performance rigid electronics may not be sufficient enough.
Do you want to take your mask off?
Yes.
Most speakers have taken off.
Then it's going to be much better.
Yeah.
Thank you. So look at the future of electronics. First, let's have a look at this section first. Bendable electronics, which is already in the market. You see, if you pay like $2,000, you can buy Samsung foldable phone. Obviously, it's way more expensive than we expected. It's really expensive. Even you can purchase rollable TV from LG if you have multi-million dollars. If you contact LG, then special arrangement can be made by paying multi-million dollars. But they actually announced this bendable TV in CAE in Las Vegas, 2019, 2020. So you can buy it. If you pay a lot more than you expected, but still the price has to come down. So this is already in the industry sector. And going forward, let's have a look at the bioelectronics. So for bioelectronics, we have much more things to consider. So in bioelectronics, you put the electronic component. We try to make electronic component interface with the human body so that we can monitor all the information from human being. For that, obviously, electronic component has to be conformal, has to be conformally coded on your body. So flexibility is a must. At the same time, you really want to have a multifunction in one small location. You want to sense things from human body. You want to record things. You want to memorize things from human body. You want to send the signal, send the health information to the centralized system, and you want to have like some sort of feedback loop so that you can deliver the drug. So multifunctionality is really needed for the future of bioelectronics. So, except for on top of the flexibility, stackability is also very important. You want to stack the different types of functions in one place, right? And let's have a look at this section. So future electronics, 3D electronics is becoming so much important because right now, the limit of the memory, size limit of the memory, and the transistor is really reaching to the atomic limit. But we really still want better computing, better memory. The only option we have is to go the Z direction. So we have to stack this up. So Samsung successfully made this, successfully made 3-dimensional NAND flash. So this is really going on. However, Intel and other CMOS company was not able to stack the transistor. You really need to have a single crystalline silicon. Then you really want to stack them up. How can you do that? How can you grow single crystalline silicon on and on? That's still is an outstanding question, but there is a possibility to have it. And At the same time, in the display industry, you really want to reduce the size of the pixel so that you can catch up with the current AR, VR trend. So size also matters in display industry. So one way to reduce the size of the pixel is to stack up the RGB, whereas currently RGB is arranged in laterally, so pixel size is quite big. So really, you really want to stack them up. At the moment, even if it's not in the commercial product yet, OLED concept was published for OLED stacking, RGB stacking, organic LED stacking was there. At the same time, edge computing is also becoming very important in the era of the smart city and IoT because we are sensing so many informations, then we really want to process the information right at the edges, right at the sensors. For that purpose, you really want to stack different types of device, for example, sensors, and the memory and processor, stuff like you want to stack them up so that you can have an edge computing task. That is kind of like a trend. So you really need to have the stackability. To satisfy all those, what kind of material is the best material for satisfying this? Actually, answer is currently, it's really hard to find the material that satisfy all those requirements. Please have a look at this chart. Single crystalline material, single crystalline wafer-based, single crystalline inorganic material performance, of course, is the best compared to the rest of the polycrystalline organic materials. However, if you try to bend current single crystalline-based electronics on the wafer, obviously it's going to be broken because it's too thick. Also, if you want to stack different types of inorganic semiconductor materials on one place, there's a big requirement. Actually, lattices of this device layer has to be matching each other so that you can stack up the different types of materials. So it's really limited, stacking different inorganic materials. It's limited because of the lattice mismatch. On the other hand, if you look at the trend of the organic electronics, even if the performance is really, really poor, the stackability, flexibility can be guaranteed. Organic is flexible and thin, you can stack, you can bend. At the same time, price is way cheaper than inorganic single-crystalline materials. So then should future electronics be relying on organic electronics? So our answer, my group answer is no. We really want to, we are really greedy. We really want to have everything. So what is the dream electronic system for the future? We want to have everything: cheap, flexibility, stackability, with high performance, with single crystalline inorganic materials. How can we do that? So for the last 5-6 years, we have been working on that, and we came up with 2 different ideas. So mission of our group is cheap, flexible, stackable, single crystalline inorganic electronics. I was really tempted to make abbreviation while I'm preparing this, but I really have to repeat it every time I say this. So 2 strategies. First, if you don't want to sacrifice performance, you obvious choice the single crystalline electronic material, then you can really make it thin and flexible and stackable by just simply peeling the active device layer, whose thickness is typically less than micron, from the wafer. Then you stack them up. Then you don't have to worry about the lattice mismatch of these materials as well. That's the first strategy. Second strategy is to scale up the 2-dimensional material heterostructure. So 2D heterostructure, this kind of term, you must have heard about it. Ever since the Nobel Prize went to the UK group that develops the way to make a graphene, this 2D material research has been boomed. Then there are so many interesting papers out of this community, and 2D material can do this: cheap, flexible, stackable electronics, because it's monolayer-based electronics. However, it's been really hard to do the single crystalline 2D material electronic component. Also, the scalability. The scale of this 2D material heterostructure is around the micron size. So that is kind of limitation. So my group was composed of these 4 subgroups to tackle this issue. So these group of people, freestanding 3D membrane subgroup and wafer-scale 2D material subgroup, are working hard to make high-quality wafer-scale freestanding membranes. Then they provide these freestanding membranes to heterogeneous integration subgroup. They mix and match different materials to make the device that has never been imagined before because of all the limitations that I just mentioned. So this group of people are making total new type of device. Okay? Then by making this kind of heterogeneous integrated devices, we are going to generate a lot of data. That data, we wish to process that data at the edges. So we also have artificial neural network group, which is AI hardware group, subgroup. But due to the time limitation, I cannot cover the whole, this four thing. So I can easily spend more than 1 hour for each group. So I try to condense everything, except for this today. I try to, cover these 3 parts today. Okay, so, all right. So let me first discuss about the 2D material, wafer-scale 2D material subgroup first. Okay, again, 2D material is promising for future of electronics because monolayer 2D material itself is stable, so it's super flexible, and you can stack up as you wish. Different material can be mixed and matched very easily. You can stack them up, right? So here is an example. So if you have a graphite, what is the graphite? Is there any people from my class? What is graphite? It's the stacked graphene, right? Then the bonding to the G direction is super weak, so you can split them up into monolayer if you are smart enough to do this, right? So this has been really difficult test. But anyways, if you can make this monolayer 2D materials, then you can really do inorganic, flexible, stackable system. But so far, there has been, of course, challenge. Ever since 2010, Nobel Prize method here, whenever you want to produce monolayer electronic component, you really need to do the taping process. You purchase the bulk 2D materials, then you put the tape, then you repeat this taping 1,000 times, then you stamp on the wafer. If you're lucky, you'll be able to find monolayer 2D material, in this case, graphene, monolayer graphene. But it's not regular, it's not uniform. You can find monolayer, bilayer, trilayer, multi-layer easily. So typical limit of the size of this monolayer 2D material is like microns. So obviously, industry is not interested in this process. So to mitigate the process, mitigate this problem, community has also been working very hard to grow 2D materials monolayer by monolayer. But so far, it's been really difficult to do so because of the nucleation growth process is really delicate here. So in order for you to have monolayer by monolayer 2D material, monolayer by monolayer growth, you first need to form the nuclei. First, single nucleation event is needed to have the monolayer. Then single nucleation event happens, then lateral overgrowth needs to happen. Then you don't want to have any second nuclei comes in. You really want to finish your growth with single nucleation event. But that is not easy at all. It ends up being multi-layer, as you can see here. That's typically what is happening. So it's really, difficult to have wafer-scale 2D materials at a large scale. So obviously then, monolayer by monolayer heterostructure can be done with this taping method at the micron scale. Obviously, monolayer by monolayer growth is impossible. So far, you cannot grow this kind of 2D heterostructure. So that's why this process is a little bit far from the industrialization, and industry has not been very much interested in this process. At the same time, it has some problem of crystallinity. Most of 2D material that you grew is polycrystalline, random orientation. All the electronic products that we have in our cell phone and computer, they're all single crystalline, but it's polycrystalline. These 3 are the major bottleneck for this 2D community to move forward. So then what are the strategies that we are taking in my group? Here, so most important thing is for mechanical peeling. Most important thing is deterministic peeling. Okay, this is trial and error. Even so, this method received the Nobel Prize 2010. We really want to be deterministic. So my group found a way to deterministically manipulate this 2D material at the wafer scale for the first time. Okay, so what's the idea here? So when you try to grow 2D material at the wafer, the case is irregular, just like I just mentioned. Then we can simply use the binding energy contrast among all the materials involved. So we try to grow 2D materials on the sapphire wafer, then we put down nickel. We sputter the nickel on the 2D material. Then why nickel? Nickel has a very high interface toughness between 2D and nickel. Okay, it has very high addition energy. So if you put down nickel, then please have a look at this addition energy contrast. 2D to sapphire wafer is weakest, so then you can easily peel them off by applying the moment to the G direction. Then you have a 2D material and nickel, then you put down another nickel on the bottom. Then you have only simply two interfaces, then you apply the moment to the G direction, crack propagate down, then it needs to find its path to propagate. But the binding energy between nickel and 2D is so much high, this crack doesn't want to split this interface. It just split the 2D to 2D interface right above the nickel 2D interface. That way, we are able to isolate perfect monolayer 2D materials right on the nickel, then we are able to transfer. With this technique, we are able to demonstrate 2D heterostructure at the 2-inch wafer scale for the first time. Regardless of the 2D material, we can do this, and very repeatedly. All right. Then, even with this success, we are not very satisfied yet because this 2D material is polycrystalline. It's really hard to grow single crystalline 2D material. So recently, we came up with a better idea, which is deterministic growth of 2D material. The idea is quite simple as well. We actually try to make some pockets on the wafer. We deposit the surface with the silicon dioxide, which provide the slippery surface. So then we only have a nucleation inside this pocket. Okay? Then we try to guide the single nucleation event inside the pocket. So before second nuclei comes in, just single nucleation event is done, then lateral growth is done. Then you got the monolayer single domain 2D materials in this pocket. This idea really worked. First, we defined the pocket, very small pocket. Then we grew tungsten selenide. Single nucleation event happens. Then lateral overgrowth a little bit. That's it. We stop. There's no additional nucleation comes in. Then we change the material. So we grew moly sulfide on top of it. So we were able to grow monolayer 2D material. This is really also first in the world. Then please have a look at this is the experimental result. If your pocket is really big, then nucleation event cannot be controlled. Single nuclei comes in, while it's laterally grown, another nuclei comes in. This is what it is. You have the multiple nucleation event here, but by just control this, you get the just monolayer nucleation. And growth is done, then we are able to do layer by layer growth of the 2D heterostructure. We are very excited about that. Intel is also very excited about that, and we are working together to make the next generation device out of this scheme. So we are about to submit this paper. However, my heart, at least, and our heart is a little bit more towards the 3-dimensional materials instead of 2-dimensional materials. So I'm sorry, Ki-seok, Doyun, Sang-hoon. I know you guys work very hard, but this is amazing. But our heart is a little bit more towards this direction because, please have a look at this chart. The electronic photonic functionality, performance, is really the best in conventional semiconductor. Please have a look at this mobility. Gallium arsenide, conventional 3-5 semiconductor, electron mobility at best 9,000. Whereas this, nice single crystalline 2D material can have like a couple of 100 mobility. Not only that, some other property also, existing 3-dimensional material has a better performance. All right. Then now, how can we have this freestanding, thin, single crystalline materials? So idea is coming from here. So please have a look at this. When we isolate the graphene from the graphite, we utilize these properties, weak van der Waals bonding for each layer for 2D material. It has a very strong covalent bonding laterally, but vertically it has a weak, van der Waals bonding. But if you look at this three-dimensional material, conventional semiconductor, X, Y, Z direction all strong. So what if we have this kind of configuration? We keep the X, Y very strong bonding, but Z direction weak bonding by putting the graphene in between at the interface, device layer and wafer interface. What if we can put it? This is kind of imaginary things initially. Then anyways, you can weaken the interface. Then you can guide your propagation through the graphene because you can suddenly weaken this interface. Then you can build them up. Then how can we make this structure, right? So think about that. So to explain this, let me just briefly discuss about the epitaxy. What is a typical epitaxy process of growing single crystalline material on the wafer? This is a process. If you have a wafer, typically semiconductor wafer has ionic bonding or covalent bonding, which is quite strong, much stronger than van der Waals bonding. Then you flow the atoms whose atomic size is quite similar to that of the substrate. You flow it. Then at the high temperature, this broken bond attracts the atoms. It forms the same lattice as a substrate. That is called the epitaxy process. Then let's have a look at this new settings. We have monolayer graphene and covalent or ionically bonded substrate. Then from the viewpoint of the atom, let's have a look at the bottom. Then this atom, what this atom sees is obviously very weak van der Waals bonding from the carbon atoms of the graphene, right? But there may be the possibility, there is a possibility that this atom can see the very strong ionic or covalent bonding force from these broken bonds. There's a possibility. Then if you flow the atoms, there are two options. One, this atom follows atomic arrangement of the graphene if this weak van der Waals bonding wins, right? Or if these broken bonds, this field can be penetrated through the graphene, then your atom will follow the underlying substrate. Two options. But already we can tell. Thermodynamically, following graphene atom is not stable, right? This atomic size is totally different, right? So this may be the case. We confirm this by doing this experiment. First, we transfer monolayer graphene on the gallium arsenide. Then we flow the atoms of gallium and arsenic in the epitaxy chamber at the high temperature. Then we check out the crystalline orientation of this gallium arsenide layer on top of graphene on gallium arsenide. Very surprisingly, we found that graphene doesn't do anything. We found that this is the case. This is the case. This bottom is the case. Even through the TEM, we found that even if there's a monolayer graphene, atomic arrangement is being followed to the underlying substrate. And more recently, 2021, we did some furthermore TEM experiment to figure out what is really going on at this interface. And we found that if you start with a arsenic finished wafer, then right over the graphene is gallium atom on top, vice versa. It's really remote interaction is going on. This paper was recently selected as a cover of the JEP. So we found that really remote interaction is existing. They're attracting each other through the graphene, right? Then this remote epitaxy concept can be perfected by having this 2D material-based layer transfer process. From now, I'm going to call it a 2DLT process. So 2DLT process really perfected this process because right after you finish the remote epitaxy of single crystalline material on the 2D material, you just simply peel, then you stack. Then from different wafer, you peel and stack. Then how can you reduce the cost of the material? You keep reusing the substrate. You're looking at the gallium arsenide membrane, which was produced by reusing single gallium arsenide wafer, which I'm having now here. So you guys can circulate this and have a look. So really, we replicate the single substrate to produce many of the gallium arsenide. It's really simple math. You can reduce the cost if you keep reusing this substrate. So we are very close to having the dream electronic system by having this. Not only that, ever since 2017, we published about that copy machine technique. We are able to apply this concept for most of existing compound materials. 2018, we applied this for 3-nitride. 2020, we applied this for the complex oxide. This concept is really working for almost complex oxide and all the compound materials. All right. Then, after publishing this, company called the TSMC in Taiwan contacted us. Hey, Jeehwan, we really want freestanding silicon membrane to do some sort of like a three-dimensional, transistor. So can you do that? So, as an assistant professor, just started, I really want to secure the funding. So I say, yes, of course, we did this for gallium arsenide, indium phosphide. Of course, silicon can be done. Just let us do this. So I asked my student, Yunjo, who graduated, hey, Yunjo, please, if you do that, we get the funding. So let's do that. So he spent a lot of time doing it. Then he came back, professor, it didn't work. It didn't work. Why? There's no reason. No reason. We have a graphene and silicon wafer. There's no reason. Please repeat it. Something may be wrong. He repeated for 2 to 3 months. He said, no, I cannot do that. So, yeah, then nothing was wrong. Maybe fundamentally it's not working. So we have to give up the funding from the TSMC. But at the same time, we made a bad story, turned the bad story to good story because we understand remote epitaxy because of that request. I really appreciate that. Maybe silicon doesn't work because silicon is not polar material. Maybe silicon is just a, elemental semiconductor which has a purely 100% covalent bonding. That may be why. That may be why. We have still 30 minutes. That may be why. So then I asked Yunjo, hey, can you do this on germanium? Germanium is also elemental semiconductor. If you bring the polycrystalline germanium, I'll believe you. He did, it's completely polycrystalline. That's right. Then this remote interaction is only allowed to the compound material system, right? So gallium arsenide luckily has a 30% ionicity, ionic bonding property, whereas 70% is still covalent bonding. That is why we can only do the remote epitaxy through the monolayer graphene. Bilayer graphene, we cannot do that. And gallium nitride, we can do the remote epitaxy up to 2 layers because gallium nitride has more polar bonding ionicity. And lithium fluoride even more, 90% through tri-layers. So we found out the ionicity really governs the field penetration through graphene. There's really meaningful work at that time. And so far, I discovered exciting things about the remote epitaxy, but there was a technical challenge, a big technical challenge. Because of this, only 30% ionicity, so field is substantially screened through the graphene, so crystalline quality is not very good. And field can be substantially screened. This means graphene formation method can completely change the story. Okay? So if you try to transfer graphene by using conventional wet transfer method, then we got a poly. You cannot do the single crystalline. Simply because by doing this wet transfer process, water trap can be there, and surface can be easily contaminated, and graphene is not flat. So we always get a poly. Only way that you can succeed on this is to do the dry transfer of graphene grown on flat wafer, which can be silicon carbide or germanium. Then you can do the dry transfer, so interface is super clean. Then you can get the single crystalline. Even so, surface is not perfect. Crystalline quality is not perfect. We recently have done the TEM to find out the gap between the remote epitaxy layer and the underlying substrate. We figure out dry transfer really reduce the gap between the epi layer and the substrate, whereas wet transfer has a much more distance. That's why we cannot do the remote epitaxy. This is, practically more severe things. We actually transfer graphene on the gallium arsenide. Then what's going to happen is it has a bubbles in manual process. It creates a lot of holes in graphene. What's going to happen is if there's a hole, then there will be direct epitaxy. The crack is not nicely guided. From that point, you're going to have the defect. So you cannot reuse the wafer. You cannot reuse the wafer. That is a serious concern. So we try to work with it by growing the graphene on the wafer. So my student, Kwang-Ye Lu, here, actually, he insists to do so. When he just first brought the result, it's really bad. So Kwang-Ye says, let's not waste our time. It's not going to work. But he insisted to grow graphene on the wafer. But it eventually works. We are able to grow monolayer graphene inside the MOCVD chamber right before growing gallium arsenide. We grow graphene on gallium arsenide. Then we grow gallium arsenide. We peel off. Then surface is perfect. We have an even pristine interface between graphene and substrate. So crystallinity is perfect. Not perfect, but surface is perfect. And it's perfect single crystalline. And this enabled us to keep reusing the substrate. Where is the substrate circling around here? Yeah, the wafer is being reused to produce the many of the layers. This is really enabler, right? And we are not very much satisfied with that. So we try to reduce the cost of the wafer furthermore. Because we can grow 2D material and 3D material in single chamber, so we can grow 2D material, 3D material, 2D material, 3D alteration all the way. Then all you gotta do, just single growth event in the epi chamber, then harvest the layer by layer. All right? This is what I have brought today. So my student Kwan and Yunpeng grew the 3 stacks of 2D material and gallium nitride, 2D material and gallium nitride. They just did only one epitaxy in the chamber. They just harvest layer by layer here. So I also like to circulate this around for you to see. All right. So I was gonna do actual peeling test here to show, to entertain you, but time limitation, I wouldn't do that. So, but anyways, you can actually just harvest layer by layer. So you can really reduce the cost of it. But there has been skepticism from the community about the remote epitaxy. Whenever I gave a talk all over the world, at least I have one question about this all the time. Every time I gave a talk. But that question is quite reasonable. And please have a look at this. Maybe remote epitaxy does not exist. If you have tons of pinholes on your graphene, then you can just do the growth through the pinholes, then lateral overgrowth finishes, then still you can peel off. That's why remote epitaxy does not exist. Right? So that kind of question has been there. All right? But to answer this question, we didn't have to do the additional work because we didn't write a paper specifically about that, but every information, evidence is embedded in all the paper that we have published so far. But to answer this question, we recently published the HTS Nano paper to show this. Actually, if the pinhole-based growth is dominating for having single crystalline, then you're supposed to have a single crystalline silicon, single crystalline germanium when you try to do the remote epitaxy of silicon or germanium. If it's non-polar material, no matter what you do, you always get the polycrystalline. Only way that you can succeed is to do the polar material. All right? Then maybe somebody asked, it's a real question from the conference. Maybe gallium arsenide case, your graphene is so defective. So if you try to do the bilayer graphene, you will still get the single crystalline because your graphene is somehow damaged. No, if you do the bilayer all the time, polycrystalline, then somebody may ask, maybe growth condition for germanium and gallium arsenide are different, so that's why you get this. But no, so gallium arsenide, if you the same gallium arsenide growth, the different gallium arsenide growth on this platform is poly. no communication because of non-polar materials there. And also maybe gallium arsenide substrate is special to make pin or no. So if you do that, it's poly. So unequivocally answered through this paper, and we are collecting more direct evidences right now to publish this. So we are very much confident about the remote epitaxy phenomena itself. But also this bad story can be converted into good story because of that we try to find a way to make the holes in graphene periodically. That way you can even do the single crystalline for the non-polar materials like silicon and germanium. Right? So we are discussing about this with IBM because they really want to do silicon heterostructure, stack them up. So this is still very meaningful. So because of that, we spend the time, we invest our time to have the freestanding non-polar material. We got it. So now we can do, we can peel any materials from the wafer. So what's the 2DLT? Going forward. To summarize about 2DLT, it produces low-cost material by regional substrate, flexibility, it has flexibility, stackability. And ever since this paper was published in 2017, really the community was being formed. So this, growth on 2D material has been, getting really hot and hot. And we first organized a symposium, first workshop about this, releasable epitaxy this summer. It was super successful. And industry has strong interest in it. Like I said, this is really dream electronic system, flexible, stackable, cheap, but it has a high performance, right? So I really want to, for the rest of time, 20 minutes, that's enough. I really want to show you guys the example, impact of having these freestanding membranes. So then you can mix and match. What's the impact, all right? So here, the next chapter, I'd like to go over our new invention in the field of bioelectronics by stacking these freestanding membranes on the body, right? So let's have a look at this chart. So bioelectronics, one of the most popular form of bioelectronic component is the electronic skin, where we can monitor the physiological information from the body using the electronic system. Then this electronic skin, E-skin, is composed of obviously sensors, which is semiconductor, and the polymer, which is skin patch, that makes the excellent interface between electronic and the human body, right? Then obviously it needs a wireless communication system. So then we can read physiological information from the computer, right? So these three components are essential for this electronic bioelectronic system, E-skin. Then what's the dilemma here? What's the challenge? Obviously, performance conformality dilemma is there, used to be there, right? Wafer-based electronics, wafer-based single-crystalline electronics cannot follow up this trend. So organic has been the mainstream for that, but now we know how to peel, we know how to bend, we know how to stack this single-crystalline material on the body, all right? At the same time, this wireless system, even if you have this imperceptible, let me repeat this one more time, imperceptible E-skin on your body, your wireless system itself is bulky. So this kind of mismatch. Your wireless system needs to have a battery and the wireless module and microcontroller amplifiers, all complicated circuits are there, which is hard to be wired, right? So that is the two dilemmas in the community. Then by applying remote epitaxy concept to this community, we are able to mitigate these problems. Here's one example. So, because we can produce the ultra-thin gallium nitride membrane every day, we try to first focus on gallium nitride electronic system. In other words, we try to bring the gallium nitride electronic system to our body. What is gallium nitride? What's the application space of gallium nitride? Please have a look at this. Most popular one to everyone is LED, right? LED light is made out of gallium nitride. UV detector, wideband UV detector is made out of gallium nitride. Power transistor, and for the communication, 5G, 6G RF filter is gallium nitride, aluminum nitride. And wireless sensor can be made out of gallium nitride. They're all on the wafer. All right. Then, how can we wear this gallium nitride on our body? First criteria is that your skin patch that makes interface to your body, skin patch and inorganic membrane needs to be attached to each other. This interface has to be stable. But then if you have a thick layer of the gallium nitride, there will be debonding. So we did some simple calculations. So gallium nitride thickness versus strain energy. And we know the work of the addition between gallium nitride and PDM and skin patch. Then with this simple calculation, it gave us, you need to have 300 nanometer gallium nitride, below 300 nanometer gallium nitride. Then you can wear the gallium nitride on the skin patch. Then, by using conventional method, you cannot release this ultra-thin 300 nanometer gallium nitride, but remote epitaxy can do. You grow 200 nanometer gallium nitride on 2D material, on gallium nitride, you peel off. You're looking at ultra-thin, freestanding, single-crystalline gallium nitride, 200 nanometer. Then you put it on the skin replica. Skin replica is conformal. It's conformal. So now we have a chance. We can bring all those systems onto our body by having this technology, right? So what is the outcome? Obviously, wafer-based gallium nitride sensor is the best. So we just bring this to our body. So this is one example, skin UV sensor. We detect the UV exposure on the skin. But single crystalline gallium nitride system is on our body. You can have excellent UV photo detection performance by having this flexible gallium nitride on the body. And this is one example. You can have the highest performance sensing on your body by bringing the single crystalline electronic system. Second, we are more proud of having this progress. By bringing this gallium nitride communication capability onto the body, you're able to completely get rid of this chip and battery to have the wireless communication. The idea is as following. We try to make the gallium nitride surface acoustic wave device. Okay? This surface acoustic wave can be generated from the antenna outside. Then depending on the physiological activity of the body, this resonant pattern can be shifted. This can also be recorded outside by using antenna. You don't need anything like this. So by having this gallium nitride acoustic wave system on the body with ultra-thin thickness, we are able to really monitor so many things from the body without having any wireless system. Please have a look at this. This is batteryless, chimless, wireless system that can do many of functions. One example, truly you have just skin patch with a GaN system on it, and you can just measure the pulse without having anything. All you need is just antenna. And you can do the sweat, sensing by coating the ion selective membrane on this GaN system. Then you can actually measure the potassium, calcium, and many other sweat component. And of course, you can measure the UV exposure as well without having any wireless system. So that is really the impact of having remote epitaxy on the bioelectronic field. All right. Also, I'm particularly proud to show this progress as well, even if my group is not specialized on polymer engineering, but we recently published this in Science Advances to show the long-term monitoring system by having the Sweatport-inspired skin patches. If you look at our skin patch, E-skin, we have this kind of dumbbell hole patterns on this E-skin. We invented this dumbbell hole pattern. What does this do? First, we drill the hole, so then we can permeate all the sweat from the body. Then by having this kirigami cut, we can make a negative Poisson's ratio skin patch. So it's really super conformal to the skin, to the body. Then, because of the sweat permeation, our human subject doesn't show any skin irritation, and mechanically really conformal and stable. And we, for the first time, shows more than 1 week monitoring, constant monitoring of the physiological activity because sweat is not accumulated between the sensors and the body. And you're looking at my postdoc who already left my group by becoming a professor, Hanner Lee, try to wear the conventional e-skin and our appropriate e-skin and try to eat the super spicy ramen. Then you see, I didn't torture my student postdoc. He liked this super spicy one. Then, sweat is being accumulated on the conventional one, but our appropriate skin, it does not have any accumulation of the sweat, and it permeates this really well, doesn't irritate his skin, and there's no malfunction of the device. All right. So here I try to also circulate this e-skin. Really, you don't feel anything, so you can have a look, and if you like, you can try to wear it. So if you like, please raise your hand. Then my postdoc Hano and Jeehwan will help you to wear it. So just raise your hand and try to wear it. Okay, so here. So Jeehwan, can you take care of this? Yeah, then just show them individually how to do that. Then okay, so if you like, just raise your hand. So you don't feel anything really. So okay, so this really allows us to integrate the single crystalline system on the body. All right. So, oops, what's happening? Sorry. This animation didn't work sometime. So, yeah, okay. So this is kind of like our wild system. It's showing the our electronic skin system. So this electronic system can track your eye movement by having inorganic system in it, and it can track your muscle activity, and it can track your pulse with this bulky wireless system here. We can do so many things, but this wireless system is really the burden. But by having our GAN system on the body, you can record pulse, physiological activity, really by not having anything. All you need is just the antenna right next to it. Then you measure the pulse without having anything. So this is really meaningful progress that we made so far for the bioelectronics field. And also, I'd like to share our progress in 3D electronics by stacking different freestanding materials by using 2D LT process. Okay, so first stack that we have tried is color stacking. Okay, so we know the challenge in display industry sector. Challenge is so LG, Samsung, or key player in display agreed upon the needs for developing micro LEDs, not the organic OLED. In the future, next trend is going to be micro LEDs instead of the OLED. If you go to Costco or Best Buy, now majority of the expensive display is OLED, organic LED. But next generation for sure, micro LED. What does micro LED do? What's the difference between micro LED and OLED? Micro LED does RGB color with using single crystalline inorganic system, right? But so far, single crystalline inorganic system was bound to the wafer, and we really need to find a way to peel them off. Then we really need to find a way to stack them up. Okay, so far there are many other options, but so far nobody was able to stack this RGB color. One of the biggest challenges, even if you know how to peel the wafer, peel the device, if you try to make a truly micro LED, like less than 10 micron, aspect ratio matters, right? If your LED thickness is a couple of microns, then you need to make a bond each other. It's really high aspect ratio. That is really challenging. That's a big challenge in the community. But by having 2D LT process, you're able to produce ultra-thin RGB peeled from the substrate. Like I mentioned, Dream electronic system, we peeled from the substrate, we stack them up, and you can never ever do the epitaxial stacking of gas and GaN together because their lattice is totally different. So you have to do it in different substrate, put it on one by one. Aspect ratio matters. So we, for the first time, shows the micro LEDs, vertically stacked full color micro LED whose size is less than 10 micron for the first time. Gio is here, who has been working very hard on working on it. When he just proposed to do this, I stopped him doing this. So difficult, Gio. Why you want to do that? But he insists to work on it, and by spending 2 years, he was able to show this. So you're looking at the world first true micro LED stacked, 3D stacked LEDs by using 2DLT technique, color mixing. It shows ideal color mixing, RGB. And he showed recently he can really push the limit to the 5 micron by 5 micron. You're looking at the 5K micro LED display. So we are really excited about that. Also, we can do the function stacking. So far, I just showed the color stacking. Obviously, we have freestanding membranes from any types of material, so we can do the function stacking. So please have a look at it. So I'd like to discuss about the magneto-electric coupling device. So for those who are not familiar with this, let me just spend like 30 seconds about the magneto-electric coupling, ME coupling device. So what does this ME coupling device do is combining the magnetic and electricity through the strain. So we have a piezoelectric material. We all know what the piezoelectric material does. And we also have a magnetostrictive material, which has a strain magnetic response. If you apply the magnetic, then it creates a strain. If you apply a strain, it will generate the magnetics, right? So recently, Intel announced the next generation CMOS by utilizing this ME coupling device performance. So if you have an ME coupling device, you can have a lowest power, logic functions. That was announced recently. Also, we can do the tunable filter, and we can do the energy harvester, and also we can do the wireless powering. There are a lot of applications in the future for ME coupling device. Then what was the problem so far in this ME coupling business? Actually, piezoelectric material and magnetostrictive material, they have totally different lattices. So you cannot epitaxially grow these two functional materials together in one place. That's problem number one. Even if you can grow single crystalline, piezoelectric, or magnetostrictive material on the wafer, you cannot peel them off. All right, two problems there. These two problems can be just solved by doing remote epitaxy. So we can do the single crystalline magnetostrictive material, single crystalline piezoelectric material, you peel off. It's free from substrate. You can maximize the strain response. Then you can stack them up. You are really stacking the different functions here. Then you're looking at looking at the strain coupling under the in-situ TEM. It's like a heartbeat. This CFO, PMMPT membranes bonded each other in freestanding way. They exchange the strain. By doing so, we are able to announce the world's best, highest magneto-electric coupling device. Obviously, it's a single crystalline, best performance. Then we couple this together to have a best ME coupling performance. This is really the last one for the application. So I'd like to share the stacking, impact of stacking for other section, which is edge computing. How can we utilize our stacking strategy for advanced edge computing? So you're looking at the very famous figure published by our friend Max Schleicher when he was in Stanford. He published about this 4 years ago. He showed this excellent edge computing task by stacking the sensor and the memory and the logic together in one place. So then you can do the edge computing task. It receives all the sensing signal, then the signal can be stored and also it can be processed. However, there's some challenges as well on this technology because each layer heterogeneously stacked layer is fixed each other, then if it's fixed, there will be a lot of problems. Each layer can affect each other, and also it will be strained, so number of stacking is limited. And also, once you fix this, making this is super expensive. Once you fix this, you cannot reconfigure it. You cannot do more, additional sensors. You cannot do additional, processors. And also, this method utilizes typical von Neumann computing method. This is just like, you receive the analog signal from the sensor, then you process with a digital. Then you need to have a, ADC, which consumes a lot of powers. Here, we try to still utilize our stacking process to make an impact on this technological sector. We stack the LED photodetectors on the wafer. Then we make arrays of LED photodetectors. Then we put down our signature AI hardware at the edges. Then we do have optical communication system, then register memory arrays, so then you can stack them up. So first you have the sensors, then you have a PD LED. So sensor signal will be transferred to the AI system. Then this can go into our artificial neural network arrays. It can process the data, and it can send another processed data to the next layer. You can stack them up, actually, freely, because of this stacked optoelectronic system. By doing so, we are really able to do the excellent, flexible, reconfigurable inference task. So you have MIT letters, pre-trained corners on these freestanding chips. Then you can just replace the chip for the MIT. Then you can recognize MIT letters, or you can put everyone together. So then you can have a sequence. We have a recognition. Then also, if you have a low photon situation, like a corrupted image, you can process it by put the denoising layer flexibly. Then you can also put different types of sensors. It's free. Okay, so reconfigurable system has been also developed by using this technique. So so I just show all the examples of the impact of the having freestanding system. So our future direction, is really interesting direction to go, and we already secure some funding for different concepts. But anyways, in the future, we have to make this material system better, and we would like to explore different material system for AI tasks. And obviously, our material is really ready. Material is really ready to move forward. Material is ready, so we are trying to mix and match. We are ready to have a lot of fun by just mixing and match different material system to have a new function, like a sensor fusion, wearable AI, brain electronic interface, and light therapy with e-skin, and so on. So so that is a future direction that my group needs to go. And obviously, I'm really blessed to have these group of people, student postdoc in my group, and they're really creative, diligent, and responsible. And really, thanks to them, we are able to, try to prepare the system that can make a new, advanced, ultimate heterogeneous integrated system. And thanks to our collaborator, also we are able to make this progress. Thank you so much for your attention.